And
I'm sorry.
yeah, absolutely. So this,
forget to the call.
Absolutely. And of course, if you have any questions during the talk, I mean, hopefully this is supposed to be an introduction to the subject. So if you have any questions, please ask away. I want to make this as clear as possible if I can. Okay, so after the last few years, there's been a lot of progress in our understanding of classical and quantum integrable systems in 4 dimensions, and I think that that's been achieved using twistor methods. I should say, I'm not sure everyone, this is a standard language to call them 4-dimensional integrable systems. I mean, perhaps when people think about 4D integrability, maybe they think about n equals 4 super Yang-Mills and the planar limits. This is integrability in a very different sense, but hopefully I'll convince you that this is really a very natural way to, that these theories really should be thought of as 4D integrable, and a natural generalization of 2D integrable models. So I think it's fair to say that this sort of subfield, this set of works was started by this paper of Kevin called Quantizing Holomorphic Theories on Twistor Space. There are a great many works in there. Lots of them are very, very important, but I wanted to just highlight this one. And this is probably the main reference for some of the main reference for the background I'll give you, although of course, as I say, there are lots of other stuff, lots of other works are relevant as well. And in this paper, Kevin introduces 2 examples of classically integrable theories in 4 dimensions and then goes on to quantize them. And those are self-true Yang-Mills theory, which maybe some members of the audience will be familiar with, and then perhaps a slightly less familiar example called the 4D Westerminer-Witt model. I'll be very precise about what these are later on. So this has sort of inspired some developments in a few different directions. So then probably one of the most significant ones is that the hidden symmetries of these 4D integrable theories have been found to be the same as some of the algebras that people discovered in the celestial holography program. And in the celestial holography program, they found these by thinking about soft theorems and amplitudes. So there's this kind of remarkable connection, which has now been sort of fleshed out in a lot more detail, most significantly by these. So there's this work of Tim Adamo, Lila Mason, and Atul Sharma, and then this paper of Kevin and Natalie Paquette. Of course, the celestial holography program is kind of a whole subject in itself, and I couldn't cite all the papers there, but these couple of papers are probably the most relevant for the connection to the things I'll be saying today. That connection can be leveraged to exploit Yang-Mills, to compute Yang-Mills amplitudes, and in particular Yang-Mills loop amplitudes in certain theories. And this was strikingly used earlier this year by Kevin to compute a 2-loop Yang-Mills amplitude, or sorry, 2-loop amplitude, all plus amplitude in a certain theory of quantum chromodynamics. Not the quantum chromodynamics of the real world, but a special theory of quantum chromodynamics, but certainly not a supersymmetric one. A supersymmetric theory wouldn't have a 2-loop all plus amplitude. Many of the things I say will be related to self-dual Einstein gravity, but that's the subject of tomorrow's talk. One of the things I'm going to touch on is that the Ward conjectured that the self-dual Yang-Mills equations kind of provide a unification for a unified way of thinking about many integrable systems, in the sense that many integrable systems arise as symmetry reductions of the self-dual Yang-Mills equations. More recently, there's been this work on 4D Simons, which is also a unifying principle for integrable systems. And these things are connected through this perspective that I'm going to talk about today. There's also been some stuff on non-trivial gauge and gravitational backgrounds. So Natalie Paquette and Nick Garner have a paper on kind of monopole backgrounds. And then there's been some work this year on self-dual Tab-Nut and the Iguchi-Hansen gravitational instanton. I'll talk about the Iguchi-Hansen gravitational instanton tomorrow. And then finally, we'll touch on at the very end of this talk some really, I think, impressive work by Kevin, Natalie, and Atul Sharma on holographic duality in an asymptotically flat space. All right, so let's start at the beginning with twistor theory. So twistors were introduced by Roger Penrose as a means of sort of encoding the conformal structure of flat space in a three-dimensional complex manifold, which now goes by the name of twistor space. And the idea is that massless free fields on space-time can be described in terms of holomorphic data on twistor space, and more generally chiral, basically chiral solutions to chiral field equations on space-time are encoded in kind of complex and often algebraic data on twistor space. And in a sense, this allows you to solve, in some cases very explicitly, and in many cases very explicitly, you can solve these kind of chiral field equations, the self-Young-Mills equations and the self-Einstein equations, using this twistor construction. Here I've added the sort of canonical picture that appears in many twistor theory talks. This is a Robinson congruence, and this was sort of, I think, part of the inspiration for the name twistor. And it was thinking about these congruences which led Roger to twistors. So let's start with the simplest example of twistor space, the twistor space of Euclidean R4. I should say in this talk, I'm going to be mostly working, almost exclusively working in Euclidean signature. But the nature of twistor space is it's a complex manifold. We're going to be studying holomorphic theories on that complex manifold. And one consequence of that is the things that we're going to compute are going to be rational or meromorphic, and they can have poles. Often they'll have poles on complexified light cones. But what that means is it's very easy to Wick rotate and or just analytically continue and reinterpret the answers in different signatures. And this is precisely how you can get to amplitudes and say, amplitudes which arise in physical theories in Lorentzian signature from starting with this kind of Euclidean perspective. The reason we work in Euclidean signature is it's just much easier to understand, well, comparatively easier to understand twistor space in Euclidean signature. So the twistor space of R4 is a rank 2 holomorphic vector bundle over the Riemann sphere, O1 plus O1. And you can recover flat space from this twistor space as the set of lines, holomorphic lines in twistor space, rational curves. So maps, holomorphic maps, CP1 to PT. There'll be a four complex parameter family of these things, and those parameters you identify with the space-time coordinates. The twistor lines, so those CP1s I'm going to refer to as twistor lines, and those that correspond to points in the Euclidean slice of space-time are fixed under a particular anti-holomorphic involution of this complex three-dimensional complex manifold. The precise form of it isn't going to be important, but crucially, it does act as the antipodal map on the base, on the Riemann surface base. And as a consequence of that, it never has any fixed points. And so if you give me a point on twistor space, I can find the image under this map, construct the line passing through both points, and then this line will manifestly be fixed under that anti-holomorphic involution. And what that does is it gives me a map from twistor space to the space-time. So you can think of going from twistor space, at least Euclidean twistor space, to Euclidean space-time as a kind of Kaluza-Klein reduction. But what we'll find is it's a very special kind in the sense that there are no kind of higher massive modes. There's only the two theories become completely equivalent without any higher sort of massive degrees. And that's really because there's some extra gauge symmetry on twistor space, which means that only the massless degrees of freedom kind of survive in the Kaluza-Klein reduction. So yeah, I guess I was kind of assuming that in what I just said, this map from twistor space to space-time, the fibers are, it gives you a fibration and the fibers are just S2s. And this allows you to think of the twistor space of R4 as just being R4 cross S2. But it's very important to understand that that's not, that's as a smooth manifold, twistor space you can think of as R4 cross S2, but not as a complex manifold. In fact, you can think of this S2 as parameterizing the complex structures on the tangent space of R4. So if I'm at a point in twistor space, that means I'm at a point in R4, and the tangent space of twistor space, and a point on the S2. The tangent space looks like the tangent space to R4 cross the tangent space to S2. The tangent space to S2 comes with a canonical complex structure, And then on R4, I use the complex structure determined by the point in S2. So as I vary along this S2, the complex structure changes on space-time. So that's absolutely crucial. And this way of thinking about twistors in Euclidean signature sort of extends to curved backgrounds. We'll see some more about later. So I want to be very, very explicit about this. Let's introduce an inhomogeneous coordinate Z on this CP1 base away from, say, the South Pole. And then the O1 plus O1 fibers, we introduce coordinates, holomorphic coordinates V0 dot and V1 dot. The dots just indicate that these are right-handed spinor variables. So they transform in the right-handed SU2. The coordinate Z is an inhomogeneous coordinate on this CP1, which is acted upon by left-handed rotations. And so the Z transforms under Möbius maps under that left-handed SU2. In the other patch, away from the North Pole, we have these other coordinates, Z tilde and V tilde, which are related to Z in the following way. So of course, this is fairly standard, but crucially, these V's, because they take values in some non-trivial vector bundle over the P1, they get a factor of 1 over Z when we go from one patch to the other. So then, as I said, points in complexified space-time give us holomorphic lines in twistor space, and we can write those out explicitly. So writing U alpha dot and U tilde alpha dot. So these are now right-handed spinors, two sets of right-handed spinors for my four space-time, complexified space-time coordinates. My holomorphic lines are given by the following formula. And crucially, it's the fact that these V's are valued in O1, which means that apparently this linear term in Z remains sort of holomorphic at infinity. So there's no, this is valid everywhere because the V's live in a non-trivial vector bundle over the P1. All right. So twistor space encodes the conformal structure flat space. And the way it does that is that points in complexified space-time are null separated if their corresponding twistor lines intersect. So for example, let's look at the origin in complexified space-time. That essentially means we set U and U tilde to be 0. So V is 0. So this is just the 0 section of the O1 plus O1 bundle. And then let's take another point, a generic point labeled by U and U tilde. For this to intersect the 0 section, we just have to set both components of this to 0. For that to be true, the U's must satisfy this condition, which is the complexified light cone through the origin. And of course, on the Euclidean slice, we'll find that our anti-holomorphic involution, for this to be sort of a real twistor line, we'll find that the U tilde 1 dot has to be the conjugate of U 0 dot, U tilde 0 dot has to be the complex minus the complex conjugate of U 1 dot. And so this will tell us that we actually are at the origin of, which of course is totally expected in Euclidean signature. The light cone through a point in Euclidean signature is just the point itself. There are no points which are null separated from one another in Euclidean signature. So the real power of twistor theory is that this doesn't just apply to flat space. That's not well, one of the very powerful. Much of the power of twistor theory comes from the fact that this doesn't just apply in flat space. This construct applies to any four-dimensional conformal manifold whose Weil tensor is self-dual. And this self-duality condition ensures that the almost complex structure that you get on the twistor space is actually integrable. Furthermore, if the conformal class of this manifold contains a Ricci flat representative, so that this is a self-dual Einstein manifold, then you can characterize the kind of twistor spaces for manifolds with that extra structure. And again, that's going to be very important tomorrow, but it won't matter for today's talk. So Penrose's student, Richard Ward, showed that there's a similar correspondence between solutions of the self-dual Yang-Mills equations and holomorphic vector bundles on twistor space, which satisfy some extra condition. And that was essentially the basis of the AHM construction of instantons. So yeah, this is really these are the illustrating the way in which sort of chiral or self-dual equations on space-time can be solved by relating them to algebraic data on your twistor space. So now I want to come on to my first example of a 4D integrable theory. I expect some of you will be perhaps familiar with this example. This is self-Yang-Mills. So the self-Yang-Mills equations are conditioned on a connection on a principal G bundle over a space-time, which here I'm going to take to be Riemannian. And in fact, soon I'm going to require that this has a twistor space. So it probably needs to be a self-dual Weyl manifold as well, but I didn't put that detail in. It's important that we're either in Riemannian or split signature, because otherwise the Hodge star operator has got it's got imaginary eigenvalues, and the Rinson signature has got imaginary eigenvalues, so that there are no compatible reality conditions. So that's why I'm going for Riemannian here. But actually, I'm just going to take G to be complex. Throughout the talk, I'm not going to worry too much about reality conditions. One can be careful about them, but I think for the ease of communication, I won't worry about them. I won't worry about them too much. So the self-dual Yang-Mills equations just tell us that the curvature of our connection is self-dual. And we can write down an action principle for this equation motion to define it as a classical field theory, and ultimately, because we want to understand it as a quantum field theory. To do that, we just introduce a Lagrange multiplier field, and just impose self-duality of F with that Lagrange multiplier. And what that means is that that field is anti-self-dual, because when we vary it, it'll pick out the anti-self-dual part of F and force it to vanish. So this is the theory that I'm going to refer to as self-dual Yang-Mills. It's a very simple theory. Because it's of BF type, it's Feynman, if we were to try and treat it as a quantum theory, its Feynman diagrams are very, very simple. It has just tree and one loop amplitudes, nothing more than that. So as a classical theory, self-dual Yang-Mills lifts to a holomorphic theory on twistor space. Now, we should expect that from the Ward correspondence. So if you remember, Ward tells us that the solutions to the self-dual Yang-Mills equations correspond to holomorphic vector bundles on twistor space. So now we're just going to try and implement that at the level of the action. And the way we do that is we write down a theory on twistor space whose equation of motion tells us that we have a holomorphic vector bundle. So to do that, we introduce this 0-1 partial connection with values in our Lie algebra. We also introduce a Lagrange multiplier field, which now needs to be a 3-1 form because it's going to have to pair with the curvature, the 0-2 part of the curvature of this partial connection. So this Dolbeault operator, d bar plus a, it determines an almost complex structure, which will be integrable if the corresponding curvature vanishes. So that's this little f is 0. It's just d bar plus a squared. And we can get that equation from the following action principle on twistor space. So again, we just Lagrange multiplier field imposing the vanishing of f. And you can actually show that this action is exactly equal to this action. Or you can go precisely from the twistor action, you implement the descent to space-time explicitly. So the way you do that is you just go to one of these twistor lines. So we look at some point on R4, we look at the twistor line, or whatever space-time might be. I guess it could be in principle some self-dual file. Conformally half-flat background. We go to a twistor line over a point. We pull back this partial connection to that twistor line, and then, then we fix the gauge where the connection 0-1 form vanishes, so that the d bar operator is just the standard d bar operator. Once we've entered that gauge, we can then integrate out components of B, which point in the space-time directions, and that will tell us that the remaining components of A are holomorphic. And it's very easy to solve that. We just write that A is the projection onto the 0-1 part of some, onto its 0-1 part on twistor space of some field connection 1 form on space-time. So strictly here, I've cheated a little bit. What I should do is I should take a connection 1 form on space-time, I pull it back to twistor space, and then I project it onto the 0-1 part on twistor space. But it's very easy to see that this is holomorphic. At this stage, the dependence of all the fields on the the twistor coordinates, the z coordinate that I introduced before, is completely fixed except for the remaining component of B. And so when we do the integral over that coordinate, we just get an integral of B, and that gives us our Lagrange multiplier field. Okay, we'll come back to talk about self-true Yang-Mills and its integrability in a moment, but now I want to introduce the second example of a fully integrable theory, which is perhaps a little bit less familiar. Sorry, is that a question? Oh. Do we have any questions? No? Sorry, I thought that might be a question there. No worries. Okay. Okay. So the equations of motion of the 4D WZW model are a partial gauge fixing of the self-true Yang-Mills equations. So first, we fix a Kähler structure on our spacetime M, which is compatible with the metric. Now, I should say, in general, given a general metric, you're not going to be able to necessarily find a compatible Kähler structure. Here, I'm going to be assuming that my spacetime is really self-true Ricci flat, which in Euclidean signature or Riemannian signature means that it's also hyperkähler. And so it certainly does have a Kähler structure. We could kind of relax this discussion a little bit and go to self-dual scalar flat. I think in that case, we'd also have a Kähler structure, but I think for the sake of what I'm saying, for the avoidance of doubt, self-dual Ricci flat or even just flat space would be fine as well. But if we choose a Kähler structure, which is compatible with our metric, then the self-true Yang-Mills equations decompose in this way. So there's a component which is 2 naught in the complex structure. There's a component which is 0, 2, and then there's a term which is proportional to the Kähler form. So omega here is the Kähler form. So the first equation tells us, and I should say, I hope this isn't confusing, that the 2 noughts here now refer to complex structure on space-time. So we've fixed a particular complex structure because we've fixed a Kähler structure on the space-time. It's no longer the twistor 2 naught. Hopefully that's not confusing. So the first equation tells us that we can attain a gauge in which the 1 naught component of the connection is 0, because this is really the 2 naught component of the curvature of just this part of the connection. Similarly, the second condition tells us that we could also attain a gauge in which the 0,1 component vanished. But of course, once I've attained this gauge, I have no more gauge freedom. So that just tells me, or at least most of the gauge freedom is fixed, I should say. There's still some residual gauge freedom, but almost all of the gauge freedom is gone. So in fact, the second condition just tells me that the connection is now in pure gauge for this G-valued object sigma, which is known as Yang's matrix. The final remaining equation is this omega F11. This tells us, this is the sort of the bit we can't straightforwardly solve, and this is known as Yang's equation. I'm sorry, that D should have an M as well. So this D bar M and dm just means they're the Dolbeau operators on the space-time. So again, we can write down an action whose equation of motion is this partial gauge fixing. And so the big difference between the action I wrote down before is that this is not going to have sort of an extra Lagrange multiplier field, which is going to behave a bit like a negative helicity particle. This is just going to describe a single sort of positive helicity gluon, but it comes at a cost. I'm not going to get the self-true Yang-Mills equations. I'm going to get some partial gauge fixing. And the dynamical field is this Yang's matrix, which is related to the gauge field in this way. So a suitable action is this 4D WZW model. This is very much like the 2D WZW model. So these J's are just currents built from the sigmas. We've extended sigma with some smooth homotopy to the identity map, and we've added some WZW type term. Of course, the difference with 2 dimensions is now my trace J tilde cubed is now, it's still only a 3 form, but I need a 5 form. And so to get the 5 form, I use the Kähler form and wedge it against that. That gives me something sensible I can integrate, and I can write down this action. And varying it, it's very easy to show that this gives you just Yang's equation. Of course, there's a cost to that, which is that introducing this Kähler form explicitly, which is that this is no longer Lorentz invariant in flat space. So it depends on the choice of Kähler structure. And in flat space, the SO4 symmetry is broken down to U2 by the Kähler structure. So this also has a twisted description. And actually, before moving on, I just want to say this theory is a lot less straightforward than the BF theory, because the BF theory, because it has this Lagrange multiplier type action, the combinatorics of, say, its Feynman diagrams are incredibly simple. But that's not true of this action. This can have much more than one loop. It can have it's arbitrary loop diagrams. So it's a much more complicated theory than the one we saw before. So classically, again, this lifts a twistor space. The dynamical field on twistor space is a partial connection, but now there's no Lagrange multiplier field. Of course, we're going to, the field equations of this action are related to the Solf-Yang-Mills equations. So we certainly want the equations of motion of our action to impose the integrability of this d bar plus a operator on a G bundle. And the natural action to use is that of holomorphic Schoen-Simons theory. So this is a very beautiful theory. It's sort of the natural analog of holomorphic analog of ordinary Schoen-Simons theory. In topological Schoen-Simons theory in 3 real dimensions. But of course, to write it down, this Schoen-Simons form is a 0-3 form, A being a 0-1 form, and the B-bar equation can be another 0-1. So this omega needs to be a 3-0 form. So really, to write this down, I need a global holomorphic section of the canonical bundle. But I don't have that on twistor space. It's not Calabi-Yau. It does, however, inherit a section which is twisted by the line bundle 04, and it gets that just because twistor space naturally embeds into CP3. In fact, you can think of CP3 as the twistor space of the one-point compactification of R4. It's the twistor space of the 4 sphere. And you can just pull back the natural weighted 3-0 form on CP3. So to write down, to try and use this to write down, to find a suitable omega, we need to introduce divisors. We need to remove the weight in O4, and we do that by introducing poles in the measure. And natural to put those at 0 and infinity. So the omega has this form. So you can see that this has got a double pole at the origin. It also, at z equals 0, I should say. It also has a double pole at z equals infinity, which you can see just by transforming to those tilde coordinates from earlier. The cost of using a meromorphic form rather than a holomorphic form is that now when I vary the action, I'm going to get boundary terms. And to eliminate those boundary terms, I'm going to have to require that the field A vanishes to first order 0 and z equals 0 at infinity. And also that by extension, that gauge transformations are trivial there as well, to first order. There's, of course, there's a second cost as well, which is that by choosing coordinates on this P1, if you remember from the discussion earlier, the points on the P1 are kind of fixing choices of complex structure on my space-time. And so when I distinguish 2 of them, and these are antipodal points on the sphere, I distinguish a choice of complex structure, and the opposite point is the complex conjugate complex structure. And of course, that's consistent with the 4D-WZW model, because the 4D-WZW model depends on a choice of Kähler structure. So that Kähler structure is determined by this choice of location of the divisor. Okay, so I claim that this really is the 4D-WZW model on space-time. To show that it's not too difficult, we should just try and use the same approach as before. So first, we attempt to fix the gauge. So we pull back to a twisted line and try to fix a gauge where the partial connection vanishes. But now we can't do this anymore because our gauge transformations are not arbitrary. They have to be trivial at z equals 0 at infinity. The best we can do is we can get it in pure gauge for some frame field sigma tilde. And there's some gauge invariant data stored in sigma tilde. And that data is the holomorphic Wilson line, which takes us from z equals 0 to infinity on this P1. And you can construct this holomorphic Wilson line at any point on space-time. And so what this gives you is a G-valued field on space-time. And that's precisely going to be Yang's matrix. Once you fix that gauge, you can integrate out the remaining components of A, and you can solve. That will tell you basically that they're holomorphic. in an appropriate sense, and then you can solve that condition. And of course, at the level of the action, you actually need to complete a square. You need to complete a square and do the relevant path integral. And this is the solution to the equations of motion. It doesn't matter terribly. You can think of this term, hopefully you can see my cursor. This term is the kind of lax matrix, if you will, of the lax matrix of a 4D WCW model. It's the partial connection in terms of the Yang matrix. And at this stage, the dependence of all fields on the Z coordinates on twistor space is determined, and we can just integrate them out. And what you'll find is you do land on WCW4. Super. Okay, so these are our two examples of 4D theories. And what I've showed so far is that they've got a twistor formulation. And I claim that this means that they're really integrable theories in 4 dimensions. So what do I mean by that? Well, I really mean that their solutions admit the action of an infinite dimensional hidden symmetry algebra. And it turns out that this infinite dimensional hidden symmetry algebra is actually the same algebra which you get by thinking about the asymptotic symmetries that arise from soft theorems. So this has been studied by, there's been a lot of work on this recently, but crucially in this work of Strominger, which followed on from some work with some collaborators, where in fact these works are mostly to do with gravity. I'll talk about the gravitational case tomorrow, but they also discuss the Yang-Mills case, and you get precisely the same hidden symmetry algebra. And this arises in a very, very natural way from twistor space. Like you can, in a sense, the twistor construction is making manifest the integrability of these theories on space-time. And a very nice way to see it is in terms of what I'm going to call the universal holomorphic surface defect. So this is the universal object which you can couple holomorphically to the theory on twistor space, which lives on a twistor line. So let me just be a bit explicit about precisely what I mean. So it's going to be a surface defect supported on the twistor line over a point, x in space-time. It's going to involve some fields which live on that twistor line. That's this J, M, N, and they depend on Z. And these are going to pair with holomorphic derivatives of the partial connection A. So I should say, right now I'm really working in the 4D WCW model, or really the holomorphic Schoen-Simons case, just because there's marginally less fields to keep track of. I don't have this Lagrange multiplier field to worry about. But we'll come to the Self-Yang-Mills case in a moment. The reason I put holomorphic derivatives here is because anti-holomorphic derivatives are exact in BRST cohomology. So in a certain sense, this is sort of the most general way I can imagine coupling my bulk theory to a theory on the defect. So this is a little bit like a Wilson line. It's a sort of a generalization of a Wilson line. So if I had say, ordinary Schoen-Simons theory in 3 dimensions, I could imagine coupling my connection, it wouldn't be a partial connection anymore, to some generators, which a priori I don't know what relations they obey. Then I would impose BRST variants of that defect. And what I'd find is that those generators would have to obey an algebra, which of course would be the Lie algebra. They'd have to have the right commutator. We're just going to do exactly the same thing. The crucial difference here is because we've got a holomorphic theory, we can take holomorphic derivatives which aren't BRST exact. So there's a much more general thing we can write down, infinitely many generators labeled by M and N for all non-negative integers M and N, and which depend on the Z coordinate. And then imposing BRST invariants, it's going to give us some relations on these J's, and it's going to say that that the generators of some vertex algebra. So at tree level, the BRST variation of the defect, it gets contributions from the following 2 diagrams. One, a bilocal term on the defect. And when I take the BRST variation of this, it turns out I compute the residue of moving this point around this point. You can remember this LX, it's a holomorphic line, so it's a 2-dimensional real thing, it's a 1-dimensional complex thing. So this turns out to compute the residue. And then there's this second diagram involving the vertex. And it turns out for these to cancel, it's a very easy calculation to show that these generators have to obey this algebra. And this is the thing I'm going to call the hidden symmetry algebra, or the celestial chiral algebra of self-dual Yang-Mills. And this is a very simple algebra. So it's just got a simple 1 over z. This means it's just the loop algebra of some Lie algebra. And that Lie algebra, I think we could call it a double half loop algebra. So these p's and q's just have to be non-negative integers. And then when I take commutators, they just add together. So very, very simple. And of course, I pick up a structure constant as well. Okay. Yeah, so we can state that precisely. So the mode algebra of this vertex algebra is just the UEA of the Lie algebra of regular maps from C star cross C squared to G. So the C star is just that loop, that dependence on the parameter Z, and the C squared are these polynomials, these non-negative integer variables. So I'm thinking of these as sort of the coefficients of some polynomial. A vertex algebra actually has more information. It's not simply just the UEA of a Lie algebra, even in the simple case where it's just got a simple goal, or where it's linear, I should say. It also comes equipped with distinguished vacuum modules living at z equals 0 at infinity, and those are determined by the boundary conditions on A. I'm not going to say too much about those, but they're important. It's important that this has more structure than just Lie algebra. Self-dual Yang-Mills, the case of self-dual Yang-Mills is very similar, but now we can couple not just to this field A, but we could also imagine coupling to B, and that just gives us an extra copy of the adjoint. So there's the algebra gets extended by some generators. They have trivial OPs among themselves, but they live in that adjoint of the J's. And because the boundary conditions on A and B, in fact, they have no boundary conditions as compared to the A from before, the vacuum modules were slightly different. So why do I use this word, celestial chiral algebra? So this has sort of been explained as part of the celestial holography program. I'm just going to touch on it here. So the idea is that the operator product of this vertex algebra is capturing the holomorphic collinear singularity in a gluon amplitude, a tree gluon amplitude in Yang-Mills theory. So I imagine I've got some tree amplitude in Yang-Mills. I've got two external positivistic external gluons. I take their momenta to become collinear in a particular way. When I do that, the amplitude will have a singularity. And this is the basis of recursion methods for computing amplitudes. And that singularity is precisely captured by that OPE that we wrote down on a couple of pages ago. In fact, it also captures the collinear singularities of the one loop or plus gluon amplitudes as well. But if you go to the one minus gluon amplitude, one loop, one minus that gluon amplitude, you'll find that it's modified actually. So the precise correspondence between the algebra and amplitudes was refined by this work of Kevin and Natalie, where they showed that the celestial chiral algebra, or the hidden symmetry algebra, it governs the collinear singularities of form factors in self-dual Yang-Mills, or in the 40WZW model. So what's a form factor? It's just an amplitude in the presence of a local operator. So let me just give you an example. It's a very simple operator we might write down in self-dual Yang-Mills is just the square of this Lagrange multiplier field B. This is a very, very interesting operator because it turns out if you add this to the action of self-dual Yang-Mills, it turns it into full Yang-Mills. Now, of course, to get full Yang-Mills, I sort of have to be able to insert that operator. I deform the action in the exponential, which means in the path integral, I have to be able to insert it as many times as I like. A form factor is an amplitude in the presence of a single local operator. So this takes me sort of one step away from self-duality. So I've illustrated Feynman diagrams contributing to a tree level form factor for this particular local operator. So this diagram on the left contributes to the MHV, 4-point MHV amplitude, which is perhaps the simplest amplitude in Yang-Mills theory. And then I've also drawn a 1 minus amplitude. So far, everything I'm saying in this section is actually classical, so I should be a little bit careful about drawing this diagram. In fact, you can see that if I take the momenta of these legs to become collinear, something interesting is happening because there's this triangle diagram. So this I should be very, very careful about. I should worry about quantum effects, which we'll come to later. But these are just illustrations of these are the diagrams that contribute in a form factor. So crucially, I'm allowed to insert this operator O, but I'm only allowed to insert it once. Okay. So what Kevin and Natalie showed is that there's this correspondence between local operators and conformal blocks of this chiral algebra, celestial chiral algebra. And then if you compute a correlator in that conformal block, so a conformal block is just a way to assign numbers to some product of generators in the vertex algebra, then if you compute some correlator, then that computes for you a form factor. And so this allows you to compute these form factors, which in certain cases will be amplitudes. So for example, you can get the MHV amplitude this way. You can actually recover amplitudes. And so, as I say, everything I've said so far is actually only at tree level, but once we've taken into account quantum effects, this can be leveraged to compute Yang-Mills amplitudes as chiral algebra correlators, and it's been exploited by Kevin to actually compute the single trace term in a two-loop plus amplitude in a certain theory of quantum chromodynamics. Bootstrap it. So without using any Feynman diagrams, just a chiral algebra computation, which I think is really quite incredible. So there are obviously some questions. Can this be leveraged? So I've mentioned the MHV, the one loop mostly, or one loop one minus amplitude, and the two loop plus amplitude. Can we get beyond? These are kind of one step away from self-duality. Can you get further? That would involve introducing more than one operator. So that's the source of the difficulty. And there's obviously the question, can this all apply to gravity? And indeed, much of the things that I just said, many of the things that I have just said and will say do apply to gravity, but you'll have to come to tomorrow's talk to learn a bit about that. Okay, so I now want to change direction a little bit and talk about Fordische-Simons theory. So Ward of the Ward correspondence.
Ask a question?
Yep, absolutely, of course.
You're talking about one loop or two loop effects in, let's say, so for the quantum field theory. But I just wondering, let's say, for the WC model are renormalizable. So if you compute higher loop effects, you encounters, I think, the UV divergences. How do you handle the divergences?
Yeah, so by these theories, I should be a bit careful about what I say, because there's definitely some work about, it might be, certainly the advantages of these twistor techniques is it allows you to quantize apparently non-renormalizable theories in an unambiguous way. So it gives you a sort of it wouldn't be.
Go ahead.
So we'll come to this in the case of the, I'll talk about this a little bit in the context of the B model in the final section, about how, so essentially what you find is something like holomorphic Simons coupled to another theory has kind of a unique quantization on twistor space subject to certain conditions. And that gives you kind of a UV that defines it. Despite its apparent non-renormalizability, yeah, but fixes the counterterms for you. Yeah.
You think that you're claiming that the theory is at least partially non-normalizable, but there is some good way to handle the regularize and renormalize the theory in a good way. So the non-partially.
Yes, exactly.
Is what you're saying.
Yes, exactly. But then, yeah, actually, yes, exactly, that's right. But I should also say, in the context of self-Drew Yang-Mills, self-Drew Yang-Mills is one loop finite. So the self-Drew Yang-Mills cases, I mean, it's certainly fine. But yes, in the case of the 4D WZW model, there's a way, basically using the B model topological string to quantize it. Yeah, and fix the counterterms. But we'll come to that. Okay, right. So Ward conjectured, well, he showed that many integrable systems arise as symmetry reductions of the self-Drew Yang-Mills equations, and he conjectured that perhaps all of them, all integrable systems, are symmetry reductions of the self-Drew Yang-Mills equations. I think now that there are examples integrable systems that maybe are too high dimensional or that people don't believe have arise as symmetry reductions of the self-Yang-Mills equations. I think maybe the KP equations are the canonical example of this, but nonetheless, many integrable systems do. On the other hand, there's been a lot of work recently on a theory called 4D Schoen-Simons theory, and that's also been proposed as an organizing principle for 2D integrable systems. So it turns out many 2D integrable models can be realized in this 4D description, which again makes the integrability manifest. And it turns out these two perspectives are actually connected via the twistor correspondence by the following picture. So the idea is you start with holomorphic Schoen-Simons theory on twistor space, which is then equivalent to our 4D WZW model on space-time. Then Ward tells you that the symmetry reduction of the 4D WZW model takes you to some 2D integrable model. And then if you lift this symmetry group, which you're going to do the reduction by, to twistor space, so this is going to be some subgroup of the conformal group, you lift it to twistor space and perform the reduction there, what you'll do is you land on the 4D Schoen-Simons theory. So this is actually fairly exotic theory. I think it's a pretty unexpected thing to write down. I'm not sure I'll write down the action in a moment, but unfortunately we don't have time to go into great detail about 4D Schoen-Simons theory. But it's a pretty strange thing, but this sort of explains why it's a natural thing to describe 2D integrable models. So I should perhaps, before going to the next slide, you might ask, why don't I put holomorphic Schoen-Simons theory here? Why not put the self-true Yang-Mills theory? Well, self-true Yang-Mills theory imposes the self-true Yang-Mills equations with a Lagrange multiplier. And so when you do the symmetry reduction, what you'll get is an action which imposes the Lax equation for a 2D integrable model with a Lagrange multiplier. And whilst that certainly is an action for a 2D integrable system, it's perhaps not, it's a bit of sort of seems a bit like cheating to just impose the Lax equation with a Lagrange multiplier. So this somehow realizes interesting actions this way. And so the simplest example is the principal chiral model. So it arises as symmetry reductions of the self-true Yang-Mills equations along a space-like plane. If you apply that to holomorphic Schoen-Simons theory on twistor space, and the way one should really do this is you should compactify on a torus and take the small area limit, I guess. That takes you to this action, pretty weird looking thing. This is precisely 4D Schoen-Simons theory. So this A tilde is, I should say, okay, let's start with the space. So R squared here is the space of the 2D integrable model on which it lives. CP1 is where the spectral parameter lives. A tilde is a connection, which is a full connection in this R squared direction, where the theory is going to be topological, and it's holomorphic in the CP1 direction. And you can write down this action. This omega here, sorry, it's not the Kähler form. It's different from what it was before. This is just a meromorphic 1,0 form. And this is determined from that form we wrote down on twistor space. So it turns out when you do this reduction, you find it takes this form, which is precisely the form it needs to take to give you the principal chiral model. And also this connection 1 form acquires simple poles in exactly the places it needs to describe the principal chiral model. So I'm afraid I don't have time to go into more detail about the 4D Schoen-Simons theory, but this is a very beautiful story. And so many integrable systems are known to arise as symmetry reductions of the self-true Yang-Mills equation. So crucially, things like affine coded theories, including Sine-Gordon, which is difficult to realize in 4D Schoen-Simons theory, and things like KDV and nonlinear Schrodinger. I believe these do have descriptions in 4D Schoen-Simons theory, but hopefully this can make them a bit more explicit, and we can connect it to the sort of the known descriptions. And I think the most interesting thing, which we'll come on to in a moment, is can we get relations between the hidden symmetry algebras? So the thing I'm about to tell you about is a kind of quantum group for self-true Yang-Mills. So a quantization of this celestial chiral algebra. It's very natural. Of course, the principal chiral model also has a hidden quantum group symmetry. It's the Yangian. So we've got this connection between the theories, 4D Schoen-Simons theory, which really makes manifest that Yangian symmetry, the twisted description. Is this going to give us relations between the quantum groups that underlie these theories? Okay, to that end, let me get to the subject of quantizing the theories. So I think the first question one might naturally ask is why one should seek a quantum theory on twistor space at all. So it turns out twistorial theories that's the name that we give to these things, have some remarkable properties, which Kevin wrote down in this paper I mentioned at the very start. So the correlation functions are meromorphic with poles on the complexified light cane, and the RG flow is periodic with period 2 pi I. So both of these things are really coming from the same place, which is essentially that if you can consistently write down an honest holomorphic theory in twistor space as a quantum theory, then its symmetries, which will be complex symmetries, are non-anomalous. So they survive as complex symmetries. And what that means is that you get complexified translations of symmetries and complexified scalings of symmetries. And of course, to have a C star action, rather than just an R star action, means that you have this periodicity under 2 pi I. And again, it gives you this result before. Another reason we should care about these twistorial theories is that they have these infinite dimensional hidden symmetries algebras. We've seen that classically, and we're going to see that it also works at the quantum level. And you can use that to compute things like amplitudes. And it can be used to quantize apparently non-renormalizable theories. So that's on the subject of the question we had slightly earlier. We'll come to that. So first I'm going to talk about self-dual Yang-Mills, because as I said before, self-dual Yang-Mills is much simpler. Actually, this slide applies to both. So both holomorphic BF theory and Schoen-Simons theory, holomorphic Schoen-Simons theory, I should say, on twistor space suffer from anomalies. So in 4 real dimensions, anomalies come from triangle diagrams. In 6 real dimensions, anomalies come from box diagrams. In 4, and of course, twistor space is 6 real dimensional 3 complex. So in 4 dimensions, usually it's only chiral fermions that contribute to anomalies. But in twistor space, everything is chiral. Because our theories on twistor space are holomorphic, everything contributes to the anomalies. So even something as simple as holomorphic BF theory has an anomaly which comes from this diagram. So these diagrams are essentially the same in both BF theory, holomorphic BF theory, and holomorphic Schoen-Simons theory. The only difference is a symmetry factor because the BF propagator is directed. So what does this mean? Does it mean that the space-time theory, say self-dual Yang-Mills as a theory on space-time is sick? No. So of course, we've known for a very long time what the anomalies of theories on space-time are. Self-dual Yang-Mills is perfectly consistent as classical and quantum field theory on space-time. Nothing wrong with it. Instead, you should view this anomaly on twistor space as being a global anomaly in integrability. So on space-time, it's clear what that diagram corresponds to. It just corresponds to the 4-point amplitude, the 4-point or plus amplitude in self-dual in Yang-Mills. So having an amplitude is no problem at all, but it does obstruct this infinite hidden symmetry. And the way to see that is we look at these holomorphic surface defects that I mentioned earlier on. I said that demanding BRST invariance of those defects determines the operator products of this hidden symmetry algebra. Well, now there's a new diagram that can contribute, which takes the following form. And this deforms the operator products, and one can check that it just doesn't define a consistent vertex algebra. The associativity of the operator product is violated. I'm not going to write down what those deformed operator products are because they're a little bit complicated. I'll be a little bit more explicit about that tomorrow in the context of gravity. So how do we get a consistent hidden symmetry algebra? Well, it's clear what we need to do. We need to remove the gauge anomaly on twistor space. We need to cancel it some way. And on space-time, that means we just need to eliminate the one-loop amplitudes. So the anomaly is actually the 4-point amplitude, but it turns out if you eliminate that one, then you eliminate the other ones as well. So there are a couple of obvious ways to do this in self-dual Yang-Mills. That's because self-dual Yang-Mills, as I said, is one loop exact. So there's nothing that can go wrong at high loop. So much easier to work in self-dual Yang-Mills. This is the only thing we need to concern ourselves with. The simplest way, or one of the simplest ways, actually the simplest way, is just to couple to enough fermions that it cancels the anomaly by running through the loop. That gives you these kind of what I think I call quantum integrable self-dual quantum chromodynamics. So there are 2 infinite families. This is not an exhaustive list. We know of some more. I don't think we have a completely exhaustive list, but these are 2 infinite families. So there's this SUN self-dual Yang-Mills with 8 fundamental and 1 antisymmetric Dirac. Antisymmetric meaning antisymmetric representation, exterior square of the fundamental. And there's a similar thing for SP2N gauge group. There are some SON examples, but there are only a finite number of those. there's at least one exceptional example. So there's these sort of cute examples. And I should say, it was in this first theory that Kevin computed the two loop full plus amplitude. So this is not, these are not just some curiosities. You can, having this infinite dimensional hidden symmetry is a very powerful thing. And it allows you to perform computations in these QCDs away from the self-dual sector, which you wouldn't be able to do if the anomaly wasn't being cancelled. There's another way to cancel the anomaly, which perhaps seems a little strange, which is to couple to an exotic axion, which has got a fourth order kinetic term. So this cancels the anomaly by tree level exchange instead of by running through the loop. So this is the diagram that cancels it. So it's an axion. So what that means is the interaction vertex looks like scalar trace f squared. And so this is just the scalar trace f squared vertex, scalar trace f squared vertex. But you can see that the sort of color structure on this thing is going to be like trace x squared squared, because it's coming from a trace f squared to trace f squared. But the anomaly was tracing the adjoint of x to the fourth because it came from a box diagram. So this is only ever going to cancel the anomaly in the cases where we have this proportionality. And it turns out that's true of SE2, SE3, SO8, and the exceptional Lie groups. And the really nice thing about this is that it cancels a loop effect against a tree level effect. So I should say, this is not a realistic description of the real world. Of course, none of these theories are realistic descriptions of the real world. The real world isn't self-dual, and it shouldn't be, hopefully, certainly doesn't seem to be quantum integrable. It's far too interesting to be quantum integrable. But nonetheless, we can compute things which are physical, using these techniques. And when I say, I should qualify that, I mean we can compute things sort of Yang-Mills amplitudes using these techniques. And the neat thing about this way of cancelling the anomaly is because you're cancelling a tree level diagram, a loop level diagram against a tree level diagram, it allows you to do certain loop computations with sort of a lower order tree computation, or one loop order less. So that's what's nice about this kind of cancellation. Of course, a fourth order axion is some non-unitary. I mean, I don't expect this to be a description of the real world at all, but these things would necessarily be just a way of cancelling the anomaly. So you can check explicitly in both of these cases that associativity of the chiral algebra is restored. So you can just check that the associativity failures you found before, they're no longer present. Okay, I realize I'm coming to the end of my time, so I'll be quick at the end here. So holomorphic Schoen-Simons theory is a much more complicated beast. It's not one loop exact, and it can suffer from higher loop anomalies. So this is not something we necessarily think about very much, but it's certainly true that you can get anomalous variations of that Feynman diagrams at higher loops. And fortunately, you can get some control in holomorphic Schoen-Simons theory because it's the open string sector of the B model. So that tells you a bit more about the theory than you might otherwise have, more control than you otherwise might have. So the first example of sort of using holomorphic Schoen-Simons theory to get a consistent theory on twistor space was this work of Witten, and then followed up for the closed string sector by this work between Witten and Berkowitz. This is this perturbative gauge theory as a string theory on twistor space paper, and they take the target space to be CP3/4, or really TT3/4, so just the subspace of it. So n equals 4 super twistor space, and because it's a subspace for Calabi-Yau supermanifold, it comes with a canonical choice of omega. And this gives you n equals 4, soft dual, n equals 4 super Yang nulls. More recently, Kevin Costello and Sai Lee show that you can consistently quantize the open-closed B model in a suitable background of space-filling branes. So this is this comment we had before about consistently quantizing and renormalization. The idea is that this theory suffers from in principle an infinite tower of anomalies, and you can show that there's sort of a unique way to quantize the theory in certain cases such that all those anomalies vanish. And it's a rather technical cohomology calculation, but it tells you that you can consistently couple, and you have to couple the holomorphic Schoen-Simons theory to a corresponding closed string sector, which is Kodaira-Spencer gravity. And there are two variants of Kodaira-Spencer. There's what's called type 1 and type 2. In the type 1 case, you have to couple to holomorphic Simons theory for the gauge supergroup OSP 8+2n/n, or in the type 2 case GLn/n. And sorry, I realize I'm going over a little bit. So sorry, these involve gauge supergroups. The only way to get an honest gauge group is in this first example and take n equals 0, and that gives you SO8. So that you can get a consistent holomorphic Simons coupled to Kodaira-Spencer. So you need to modify the construction slightly because twistor space isn't Calabi-Yau. We have these divisors. Kevin shows how to do that. Very recently in this work with Natalie and Atul Sharma, they show that Kodaira-Spencer gravity, the closed string sector, descends to something called Mabuchi gravity, which describes a sector of a partial gauge fixing of a subsector of conformal gravity. We've already seen what holomorphic Simons theory describes. And then the really incredible thing that they do is there's this notion of holography for the B model. And this is the B model on twistor space. And so using that, they get a holographic duality between a theory on space-time, which is not quite flat space. There's some back reaction because they're doing holography. So the brain saw some back reaction, which gives you some asymptotically flat space-time called Bern space, Euclidean space-time. And then that's got a holographic dual. And so you get this kind of explicit example of flat holography. All right, and then there are some questions, but in view of the time, I think I should stop there. So thank you very, very much for listening. Please, if you have any questions.
Yes, thank you very much, Roland,
Fire away.
for very interesting talk. So now it's open for discussions. So is there any questions or comments?